Okay. Okay, so good afternoon, everyone. And first, let me thank the organizers to give me the opportunity of being here. It's a great pleasure. And the topic of my talk would be efficient quantum state tomography from an experimental point of view. And in particular, I will talk about this work we've done in collaboration we at the University of Rome Sapienza. We've done in collaboration with the University of Texas, Austin, and the UCL in London, where we experimentally realized learning scheme for quantum tomography, which is which is exponentially better than the traditional learning schemes in the number of measurements, at the price of being only giving only approximate results. So let me start by briefly recap how generic quantum state tomography scheme works. So we have a process, a physical process that produces a given state, a given quantum state, and we suppose we can perform some measurement. Now we can suppose are two outcome measurements on the state, and after gaining some statistic using several copies of the state, we get the outcome E1 EM, and from this outcome we can reconstruct using some procedure the density metric description of the state. Now, these procedures can be is by no means unique, as you know. There are most common procedures are probably linear inversion and maximal likelihood estimation, but also Bayesian estimation and some interesting properties. These procedures have their drawbacks and their strong points, but they all have in common that they have a measurement complexity that increases exponentially with the number of qubits. By measurement complexity, of course, I mean the number of measurements needed to reconstruct the state. In particular, it scales at 4 to the n. So this means that 8-qubit state already needs more than 65,000 different measurement bases, and if we go up to 10 qubits, we are already over 1 million. This is a serious experimental problem. It means that it's experimentally challenging to do a state tomography even in, for example, 8-qubit for a 8-qubit dimensional system. But also, it can be seen also as a theoretical problem, because it means that my theory somehow to make prediction needs an exponentially increasing number of observation, which can be a bit strange. So at first, yeah. Different kind of measurements, different bases. So not samples. And now, to be fair, there are some different reconstruction techniques that can accomplish better scalings for some common class of states. So, for example, there are results for states or for matrix product state, which I'm sure this audience is well aware of. And but for a generic quantum state, there is no way of overcome this exponential scaling. I mean, it's just what we expect for a quantum state. It's this exponential complexity of why we like quantum states in the first place. So, but if we approach the problem from a different point of view, we could ask ourselves what is actually a density matrix. It's it's a device which we use to make predictions for our system, given some previous observation. So what if we ask our scheme, our procedure to not to be able to predict all the measurement we do on the state, but to predict only most measurement. Well, if we do that, there's a nice result which was published in this paper, which dates back to 2007 from Scott Aronson, in which he proved that you can do this with linear measurement complexity. So with just a number of measurements that scale linearly with a number of qubits. Before going ahead, we should define what we mean by most measurements. So to do that, to define it more precisely, we can think of our measurements as chosen randomly from a given distribution D. And so what we want to do is to be able to predict the outcome of this measurement with high probability on given this distribution D. So what we want to do is to okay. What we want is that the probability of failure of a prediction with a given accuracy gamma is less than a hopefully small constant, small value epsilon. So how the scheme works? First, we choose a set of m different measurements, which we call the training set, randomly from the distribution D. And we perform this measurement on the system. Then we find an approximate density matrix sigma, which has just to be a density matrix such that its prediction do not differ from the one made with the complete density matrix rho, at least for a value eta. And this should be valid for all the measurements in the training set. So if we do that, if we find this matrix, sigma, then we have that probability with a given probability 1 minus delta, this sigma, this matrix sigma generalizes to other measurements done on the system. So we have what we want. It's that the probability of failure, given a certain accuracy gamma, it's less than epsilon. All of this works if the number of measurements in our training set is more than this quantity. So this quantity actually gives my measurement complexity. We can take a closer look at it. So as I have anticipated, it's linear with the number of qubits, with this n. And it depends on all the parameters of the learner, of the learning procedure. But when I see this quantity as an experimentalist, I immediately worry about the value of this constant k, which is not specified by the theorem. Because if this value is too large, this would mean that maybe this disadvantage of our standard tomographic techniques starts to work after a large number of qubits. So that would have no practical applications right now. And another thing I worry about is the dependence on gamma and epsilon, which we need to be quite low. I mean, since they are my accuracy and my probability of failure. Now, Aronson proved that you can improve the dependency on gamma and epsilon at the price of increasing the dependency in n by this logarithmic factor here, which is not too bad for. Yeah? Yeah? Yeah. All the measurements sample, I mean, you take a training set of measurements, and then you want to the sigma to generalize to all the measurements that are in the distribution D, with the probability that is given by the distribution, by your distribution. Yeah, it can be very general. It means it. I mean, it's one of the parameters you have to choose. What measurement do you care about? That's what the distribution tells you. What measurement do you care? Do you want your procedure to be able to predict? Which are most important? Which less? I mean, that's what the distribution tells you actually. Yeah. Yeah, it is, but yeah. Well, actually, I do not have an answer for that, but yeah, yeah, clearly. Yeah. It should depend on the distribution, but I don't have an answer on how exactly it depends on the distribution. So okay. So still, we have we have improved this dependence on gamma and epsilon, but we still don't know this k, and we thought the best way to see if it was useful in practical scenarios was to apply to a practical scenario. So that's what we did. And the first thing you notice is that the theorem does not even give you a procedure, an algorithm to compute this matrix sigma. So this leads also to the question, is there an efficient algorithm to do that? Of course, this is another kind of efficiency. I mean, this is not efficiency in the number of measurements, but still. And we can compute the sigma with a convex program, which, as we know, is a polynomial in the input size. So it is efficient, but in the input size. So it's not in the dimension of qubits, which is exponential in the input size, which is logarithmic in the input size. It can be proved that for special kind of states, special class of states, the sigma is actually efficiently computable, in particular for stabilizer states. But in the general case, it's not. And we used in our work an algorithm which is due to Elan Azan, which makes no such assumption. So this is for the general case. Okay, let's move now to the hardware. We tested this this protocol on two different photonic setups, which uses a different degree of freedom of photons. In the first one, we used the orbital angular momentum and polarizations, and the second one, path polarizations, to generate GHZ states with 4 and 6 qubit. Let's see the first setup in more details. Okay, here we have NSPDC series, which produces a pair of entangled photon, which then are manipulated by quarter-wave plates and Q plates to generate an entangled state in polarization and OAM degrees of freedom. These Q plates are just birefringent pattern slabs which are in a way similar to the SLM, which was presented 2 talks ago, but is specialized for the case for the OAM manipulation. So after that, we analyze the states first in polarization with this polarization analyzer, and then again with Q plates to analyze the OAM degrees of freedom. In this way, we can generate this GHZ state where R and L represents the right and left circular polarizations, and +1 and -1 are the eigenvalues of the corresponding OAM eigenstate. And we can measure all possible combinations of Pauli observable with this scheme. So which is the measurement distribution D as the uniform distribution for on all the stabilizer for this state. We did that to make the task of learning the state more difficult for the learner. Because if, for example, we choose a uniform state on all the possible combination of parallel observables, it would have been easier for the algorithm and more trivial, because probably at least for low accuracy, a state not far from the completely mixed state would have do the trick. So this makes the problem more difficult for the learner. And about the second setup, here we use the two SPD sources, and which produce two entangled pairs of photons, which are then further entangled by means of this fiber-based PBS. With this scheme, detecting four-fold coincidence, we can generate a four-photon entangled state in polarization. And then we further increase the dimension of the state by entangling polarization and path degree of freedom using these Sagnac interferometers, which acts both as a generation device and analysis device, while retaining a good phase stability. So with this setup, we can generate this state. H and V are horizontal and vertical polarization, while A and B represents the two paths in the Sagnac interferometers. But we can measure only the combination of sigma Z and sigma X Pauli observable. So this time we took the as before, the uniform distribution on the stabilizer, but only the one that are combination of sigma X and sigma Z. Okay, let's go to the results. Here you can see the probability of failure, which we can see it goes down pretty quickly with a number of measurements in the training set, M. And each one of these points represents an average of several trials made with different training sets. And we use it as an accuracy, which is the 0.1. So, but maybe another benchmark for our scheme is to try to test our approximate density matrix sigma with the complete density matrix, which was obtained by usual maximal likelihood estimation. We can see that this density matrix, this fidelity between the two matrices also goes up pretty quickly with the number of measurements n, while the fidelity between this matrix and the completely mixed state, which is the starting point of our learning algorithm, goes down also pretty quickly. But this thing is not, as I was saying before, this thing is not true in general. Indeed, is not guaranteed that the approximate density matrix sigma will be similar to the complete density matrix rho. The theorem does not give any information on how sigma will be. It just says that the prediction will be similar. Okay, so finally, here's the wanted to demonstrate. And we can see the orange one are the theoretical simulated point, while the green ones are the experimental ones. And as we wanted to show, this approach is feasible for even for low qubits states. And for example, for 6 qubit state, we need only seven measurements with this parameter. Yeah. So it's it can be applied in practical scenarios right now. Okay, so since it seems there is no more time, I will just skip this too. Those were two other works also by Scott Aronson, which came out recently after our work, and which are two different tomographic schemes, which kind of improve the ideas of this one. So we have demonstrated that we can apply this this protocol in a real scenario, and that the that the scaling is actually a linear scaling. But still, even if this protocol is very general, it should work for every quantum state. We only applied it to a very specific kind of state. So what we would like to do now is to try to test it with different states and different different kind of measurements, and of course with higher dimensionality systems. Another thing which would interesting to do is to try to implement these sort of protocols I was talking about, which, okay. So I think that's all. Thank you for your attention.